Okay, so hello everyone to our weekly seminar. Today we are very grateful to have with us Dominik Schleider from the Universidad de Concepción in Chile. Just to give you the usual summary, Dominik got his PhD in astronomy in 2009 in the University of Heidelberg in Germany. Afterwards, he moved to the Leiden Observatory in the Netherlands and later went back to Germany to the University of Göttingen. And since 2015, he's a professor of astronomy in the Universidad de Concepción in Chile, as I said. He's a recognized expert on the physics behind the formation of astrophysical objects such as stars. And today he will talk precisely about the formation of the first supermassive black holes. So thank you very much, Dominik. We are very happy to have you here, and the floor is yours.
Yeah, many thanks for the invitation. It's a big pleasure to give this colloquium in a nice way, even if it's not presential, to come back to Trieste. I mean, where, as we just said, I've been there quite some time ago as an undergraduate student, and it was a big pleasure. It's been really very beneficial, and we learned many things. And I think, in fact, the work that we do now might be actually more closely related again to what we learned in Trieste at the time about gravity and about many other interesting subjects. Yeah, what I want to discuss today is essentially the formation of the first supermassive black holes. And I mean, mostly from a large-scale point of view. So the main question that we will ask is, how can you actually accumulate enough mass from large scales to the small scales so that you can form a central massive object that has such a high mass? And that is something that we've been working on over quite a number of years. And yeah, where we've been exploring different types of pathways that are proposed in the literature. I briefly want to show you also our theory group here in Concepción, because it's one of the largest, or it could be that we are currently the largest theory group in Chile, at least in astronomy. We have 3 postdocs. We have quite a high number of master students. It's currently around 10 master students, and it keeps increasing, which at a certain point will be a problem, which in principle is also very positive. And we have PhD and undergraduate students and working on quite a range of topics, so several of them working on formation of massive black holes, but also black hole accretion or radiation transport in black hole environments is something we work on. And also different things like modeling dynamos in stars is what some people in our group are doing. Yeah. But now to the problem of supermassive black holes, I think you know that there is now a very large number of supermassive black holes at high redshift. The highest redshift black hole that we know is at redshift 7.5 and has 8 times 10 to the 8 solar masses. The most massive supermassive black hole has 12 billion solar masses and is at redshift 6.3. And in total, in 2016, there were already more than 100 quasars at redshifts larger than 5.6. I think by now this number has even doubled. So now we have around 200 quasars at redshift. So there's a very strong development in observational astronomy. And it's in some sense clear that while these quasars may not be exactly common, at least a significant number of them has been around in the early universe. And the question is, of course, what is the origin of these quasars and how do we explain them? And at least it seems to be somewhat difficult to explain them by accretion alone. One of the reasons is basically related to the way that we think that accretion works. If black holes accrete rapidly, typically we expect them to have a relatively high spin, and black holes that have a high spin, they typically also should have a high conversion efficiency of accreted rest mass into radiation, which then, if you consider Eddington accretion models, can limit the growth of the black holes in a relevant way. You see this here in this diagram from Stuart Shapiro, which he created quite some time back. And it shows basically the final mass of a supermassive black hole divided by the initial mass, where the final mass is being evaluated at a redshift 6. And Zi here is the initial redshift when the black hole originally formed. So you have basically a redshift range from redshift Zi, the initial redshift, until redshift 6, where the black hole is allowed to accrete. And what happens here depends very strongly on the efficiency parameter. If this efficiency is very low, then yes, the black hole can grow by many orders of magnitudes. But if you have more realistic spin parameters like 15 or 19 or so, then maybe you can do 3 or 4 orders of magnitudes, but doing more than that is difficult. And if you turn this argument around, then of course it implies that you need to start with a very massive C to begin with. So if you can grow like 4 orders of magnitudes in mass, then the initial seed would have to be even 10 to the 5 solar masses, for instance. Yeah, so that's at least one argument in favor of massive seeds. There are some potential ways maybe around it. Of course, there's also discussion on super Eddington accretion, and this could also be a way to potentially resolve this problem. But on the other hand, it is also getting a bit more tight as we have supermassive black holes now at redshift 7.5 rather than 6. So at least we'll need some mechanism to get them in place early on. And good, I mean, the pathways to form supermassive black holes, at least the basic ideas have been sketched quite a long time ago in 1978 by Martin Wies. And I mean, he considered quite a vast range of possible models. So this includes, for instance, what is called a direct collapse of a massive gas cloud, which via relativistic instabilities could collapse either directly into a supermassive black hole, or there could be what is nowadays more likely or more frequently considered. There could be first the formation of a supermassive star, which then subsequently should evolve and contract until it becomes a supermassive object. This is one of the scenarios that we will talk about to see if or under which conditions it's feasible. The alternative, of course, is if the cloud rather forms stars and you get very dense stellar clusters, then these clusters in principle also could provide conditions under which a massive black hole forms. And this is an alternative pathway that, that we will also consider. I think on both of these pathways, we had quite some progress, but we are also not yet at the end of understanding on what's the final conclusion. But good, maybe we can discuss about it more towards the end of the talk. Yeah, here this is just to give you also a slightly more recent point of view. I mean, it's still very much related to the original ideas of Martin Wies, just more in a cosmological context where you start with mergers of small halos forming a massive one. And then depending on the environmental condition, if this halo goes through atomic hydrogen cooling, people expect that it would contract more gradually, more slowly, and that it might form only one single object, at least in the most optimistic case. While if there is efficient cooling, it's very likely to strongly fragment, form stellar clusters, and then you need to rely on collisions to form a massive object. And I mean, in principle, these are still the main pathways we consider nowadays, even with some variations in them. So you find different types of sub-flavors of the different models. A possibility that has also been considered, which is somewhat unrelated to these two extreme cases, is just whether the supermassive black holes could be a result of the first stars. The first POPs-V stars at some point were considered to be quite massive, and there are some studies that show that populations V stars, at least in rare cases, could achieve masses that are slightly beyond 1,000 solar. I mean, these are results that are still somewhat controversial in the literature, like the result here has been based on a 2D simulation. And of course, a 2D model will have problems to capture fragmentation in a perfect way. So I don't think we should take these numbers as for granted. I think it's in a sense an upper limit on what could potentially be reached. I mean, good, if we consider populations V stars in this mass range, then in principle, if you consider stellar evolution models of POPs-V stars, then indeed there is a mass range, say, between 300 and 1,000 solar masses, where these stars would collapse into a massive black hole at the end of their life. Or there's another range between 30 and roughly a bit more than 100 solar masses, where you can also form black holes from POPs-V stars. So in principle, this is something that can work, even though people also pointed out quite a significant number of problems in the literature. The main one is related to the feedback, because if you have a populations V star with 1,000 solar masses, the radiative feedback will be very strong. And it's very likely that the halo will be evaporated by the POPs-V star itself, and that there won't be mass left to be accreted. So you would have to find then ways to work around it, either to have a merger very soon which brings in new material. This could be one way to potentially get this to work, but it is still controversial in a sense whether this is the right pathway. But perhaps to give a bit more of a general idea, if we want to understand under which conditions we can form massive objects, and how this could depend on the environment and on different factors, a study that shows us some very important aspects on how fragmentation works. Good is this study here by Lee et al. From 2003, where they've been varying the equation of state in simulations of turbulence, which include the self-gravity of the gas. And they've checked equations, they use polytropic equations of state with different parameters gamma. So from gamma equal 0.2, which means effectively that cooling is very efficient, that the temperature decreases rapidly with the density during the collapse. So then even pressure will not be decreasing, but at least it doesn't increase very significantly during the collapse, while gravity tends to get stronger and stronger, and then the Jeans instability becomes more efficient. And what you see here in this plot on the left is that you form many fragments, and that you get a spectrum of masses. Most of them peaked at relatively low masses, maybe a few that go to somewhat larger masses, and in general a quite high number of objects. If you change the equation of state and you make it isothermal, for instance, with gamma equal 1, then you see that the peak moves from here more towards intermediate masses, and the number of fragments is decreasing. You still get quite a number, but it's a reduced number of fragments. And if you have gamma equal 1.2, so if the temperature even increases in a relevant way during the collapse, then at the end you form only very few objects, and those are then at high masses. So in principle, this tells us that the equation of state has a very strong impact on the mass distribution that we can form. A polytropic equation of state is, of course, still a strong simplification, because if we consider gas collapse over many orders of magnitudes, you will enter different regimes of cooling and of the equation of state. And I mean, this is what we nowadays model when we try to follow how collapse and fragmentation occurs. Good, then you can in principle get more complex behaviors. But this just is an initial idea. To explain also, I mean, about what are the thermodynamical regimes that we can enter. This here is still based on a 1D or a one-zone model of the evolution in primordial gas, which considers the chemical evolution and also the cooling and heating processes during collapse. You see here the temperature as a function of the number density in the center of the cloud that is here considered and which is undergoing a free fall collapse. And this is in principle considered in the presence of a soft UV background, so where the spectrum extends up to a frequency of 30.6 electron volts. So it's a non-ionizing radiation, but what it does is that it dissociates the H2 molecule, which is the main coolant in a primordial gas. So it has a very strong impact on how much the gas can cool. And good, in principle, this is a radiation that is that one can show that should be able to permeate deeply into the primordial gas, because overall the cross sections for this radiation are relatively low. If we go to ionizing UV radiation, this will usually be trapped locally, at least in the early universe, while the soft UV can travel much larger distances and can therefore also affect how the formation of the first objects will occur in more distant places. And good, you see here that there's quite a range of possibilities. First, if we have J21 equals 0, so no radiation background, then good cooling is rather efficient, at least under early universe conditions. You see that the gas, even at the maximum, it is still much warmer than a present-day molecular cloud. In the Milky Way, clouds cool mostly via dust grains and via heavy elements, but we don't have these heavy elements in the early universe. And so the lowest temperature that we can get is around 300 Kelvin. If in addition we destroy the molecular hydrogen via soft UV radiation, then you see how the temperature may increase further. And you can get up to around 10,000 Kelvin or so, which is slightly then decreasing as a function of number density. So good, one thing that you can see in this plot, even though there is some room to actually increase the temperature, the equation of state, even in this extreme case here, is still, it's not isothermal. There's a small decrease of temperature with a number density. So even like in the most extreme case, this tells you that in principle, the conditions are not ideal to, I mean, we can certainly not prevent fragmentation here. It's likely to still happen. It will be less fragmentation compared to more extreme cases where cooling is more efficient, but it's still going to be relevant, and we can't ignore it in principle. But good, of course, nevertheless, what we can see is that changing the thermal conditions can have a strong impact. You see here these diagonal lines which indicate the Jeans mass under different conditions. The Jeans mass depends on the temperature and the number density. And you see that here we start with a Jeans mass of 10 to the 6. Then here it goes through 10 to the 4, 10 to the 2, and 1. So the Jeans mass depends on the density. It's mostly driven by the density evolution, but also by the temperature. And so if we look at a constant density, you basically see that say if we consider here density of 10 to the 6, then good for if you have H2 cooling, very good in the case of H2 cooling. Yeah, you could have maybe a Jeans mass around 10 to the 6, while if you go higher to the atomic cooling regime, then instead you are on the dashed line here, where the Jeans mass is 10 to the 4. A moment, I should have compared 10 to the 4 with 10 to the 2 here. So, I mean, you can get about 2 orders of magnitudes in the Jeans mass, at least naively. It depends then at what densities fragmentation actually happens, which is related also to the dynamics in the problem. But good, it tells you that at least potentially the thermodynamics can have a relevant effect on fragmentation. And good, I want to show you now some simulations that we did to test direct collapse with numerical simulations. These were simulations done with the adaptive mesh refinement code ENSO. It's a cosmological simulation code that includes dark matter and the baryons, and we included models for primordial chemistry and even for models for unresolved turbulence. We focused here on gravitational collapse in 10 to the 7 solar mass halos. So these were zoom-in simulations where we employed many refinement levels to be able to look into smaller and smaller structures which form dynamically, and where the refined grid is forming dynamically during the runtime of the simulation as well. Once we reached high densities, we changed the equation of state. We switched off the density, the chemistry here, and turned the evolution adiabatic to mimic the formation of a protostellar core, and which basically allowed us to study how mass is accumulating there in the central region in an object, that one can consider as an approximation for a protostar. And initially we considered very strong radiation backgrounds in our studies, but I will also show you results with different radiation backgrounds. And could you see here first the halo structure after the initial collapse? In the density, you essentially have mostly a power law profile. This is very similar to what you expect from an isothermal sphere. And it makes sense because the temperature here is almost constant. Initially, when the halo forms, there's a virialization shock. This is what you see here in the temperature, which is this increase that happens on the large scales. And then after that, the temperature is almost constant. Good, we have different energy components. You see here, for instance, the subgrid scale turbulence that is in the simulation, which has some variation on our numerical resolution, but not very significant. And you see here the behavior of total energy is a function of radius. After about 4 freefall time, our central region has evolved in a relevant degree. We see here results of 9 different simulations, and in each of them we've been studying what can happen in the central region, what types of behavior do we find, and we see that even after a relatively short time, in principle, this is still an early stage. We do see quite a couple of examples where fragments have formed. We also see that there are filamentary structures from which the central clumps are accreting. We see that sometimes we see signatures of disks around the most massive objects, often with spiral arm structures, which are related to instabilities that are driving the accretion. So we find quite a large range of physical phenomena here. In principle, we also saw from these studies that the accretion rates in this regime, they are quite high. So we have here accretion rates of like 1 solar masses per year. These accretion rates initially were a bit of a surprise, but they are confirmed now by other groups as well who did similar simulations. Of course, it's important to say that these are accretion rates that happen under very extreme conditions. So if the external radiation is so strong that you prevent the molecular hydrogen from forming. Yeah, this here is a bit more zoomed in. So here you see even the central structures a bit more clearly with the spiral arms, and yeah, perhaps it helps to imagine that there's indeed very strong accretion going on. Now, if we change our external radiation field, if we allow this to vary, things can in principle change by a very significant degree. If we focus first on this plot here on the right-hand side, you see how the thermal evolution changes when you vary the J21 parameter, which parameterizes the radiation field. So if we consider the black line here, for instance, in this case, yeah, molecular hydrogen cooling kicks in relatively early. The gas becomes much cooler. We go down to temperatures of around 300 Kelvin. So the thermodynamics change very significantly. And we did simulations on that as well to study what are the masses that can form. And good, even if we consider relatively long time scale, so we've been advancing some of these simulations for like around 100,000 years. Good, then in the more moderate cases, we form objects that have around 1,000 solar masses, while good for the more extreme cases, when molecular hydrogen is fully dissociated, we are around 10 to the 5 solar masses, at least in the most optimistic cases. So good, in principle, this tells us that good, there is a bit of a range, at least. I mean, we do not depend exactly on having the hydrogen completely destroyed. There's in principle, the objects are less massive if we diminish the radiation background, but there is still, at least one can still form moderately massive objects in principle. So this in principle, this can be useful. Even so, yeah, moment, I should show you this movie here. That's a very recent result from one of our cosmological simulations, where basically we study the collapse from from an early stage, and we zoom in until the gas reaches a very high density. So just to give you an idea how these simulations work and evolve. We see here the time evolution, and you can follow on the y-axis, or you can follow on the axis here how the density scale is changing and how the density is increasing. We have now some fragments that are about to form. Sometimes they also tend to be ejected. So this is an effect of like 3 body ejections. And in this way, you can lose some of these clumps, but you also tend to form new ones. And I mean, what you typically get from that is then a mass distribution. You don't form one single object that is very massive, but it's quite likely that you have several, that you can have binary systems, or even more complex systems, so that you have you could form dense stellar clusters that include some particularly massive objects. So we also saw results where you end up with a very strong and wide mass distribution. Momentum. Want to go to the next slide. It seems the presentation. Oh yeah, okay. Now I'm at the next slide. A problem that I also want to show is that good, if we to get to the stage where molecular hydrogen is fully dissociated, this depends quite a bit on what you assume for the spectra. And what we also saw is in our simulations, once we consider more realistic spectra that are more adequate for population 3 stars, the strength of the radiation background that you need, it tends to increase significantly with the spectral temperature. So you need radiation backgrounds of yeah, at least like 10 to the 4, or actually a bit higher than 10 to the 4, if you want to produce, if you want to fully dissociate molecular hydrogen. The blue line here, this is what we found from our 3D simulations. For comparison, we've shown here the black line. This is what other people derived before from one-zone models. And you see here that there's a difference by 2 orders of magnitudes. And the reason for that is that if you do only the one-zone models, you're missing a large part of the dynamics. You form the virialization shock in the beginning, where a lot of the where a lot of the hydrogen is ionized. And if you ionize the hydrogen to a certain degree, you create a large number of free electrons, which then at high densities, they stimulate the H2 formation, because H2 formation in primordial gas is regulated by free electrons. And if you don't incorporate the dynamics well, you're missing this process. And you see here that it makes a very significant difference. And that's that's one of the reasons why it's very important to use 3D simulations in this context. But the problem, of course, is if you require such a high value of J-quid to dissociate molecular hydrogen, you do get statistical problems. This is a study by another group, by Mark Dijkstra, who basically try to make predictions for a given value of J-quid. What is the number of supermassive black holes that we can form at high redshift? And you see that for instance, here, these black circles, what you see here, this corresponds to a value of J-quid equal 100. If you have a lower value, J-quid equals 30, it's these red circles here, then you can get a larger amount of supermassive black holes. And good for comparison, the solid line here, this is the number of supermassive black holes that we know from redshift 6. So the models in this case with J-quid equals 30 or 100, they tend to over-predict the abundance. But if instead we have to take a value like 10 to the 4, we are somewhere well below the bottom of the diagram. So it's basically, there could be a very significant problem in matching the observed abundances. And well, of course, the last word is not necessarily spoken. And we also have simulations that show while fragmentation occurs, the fragments can potentially merge. And there could be ways out of these problems. But nevertheless, it's important to also consider other scenarios. And this is what I want to show you in the remaining part of the talk. You see here, this is an early point of view on what could happen in stellar clusters. This is work by Bernadetta De Vecchi, who worked on analytical models to study black hole formation in the first stellar clusters. And using analytical estimates, she was showing that objects with about 1,000 solar masses could form in these clusters. And this is something that is now also being checked more and more in numerical simulations. There's been additional relevant input recently also from stellar evolution models, or protostellar evolution models, I should say, because people have shown with protostellar evolution calculations that the radii of these first objects that form, at least at the time when they are rapidly accreting, these radii are considerably enhanced. And so you see here from these plots that you can have radii up to like 10,000 solar radius or so, which of course this is an extreme case, but there's quite a range of possible and relatively large radii. And of course, if you have such large protostellar radii, in principle, it considerably increases the probability that you could have collisions. It makes it more likely for fragments or for protostars to merge. And So in principle, considering collisions indeed could be a very important part of the problem, and yeah, is something yeah, that we need to take into account. Here you see the results of this was a very first study to explore in-body collisions numerically in primordial clusters, where we've been in principle parameterizing how strongly the results depend on the protostellar radii that we assume, and good also on the number of particles in the cluster. It depends also quite significantly on how much time we have for evolving the cluster. If we assume that it's about 1 million years until the most massive stars explode due to feedback, then it is still difficult to form very massive objects here in the typical clusters. You would then have to go to the quite extreme upper end of the radii, and you would need many particles. If you have more time, if you have up to 10 million years, of course, the most extreme results you always get in the for the more extreme parameters, but you can get enhancements of the masses by factors of between 10 and 100, also in a more intermediate regime. Good in principle from this first study, we saw that collisions can have some effect. Even so, it depends, of course, on your environmental conditions. If you consider a very compact cluster, then potentially you may even be able to achieve conditions where collisions alone can do the job. It depends very strongly on how much total mass you have in the cluster and how compact you're willing to make it. Of course, but one thing that we also did is we were trying to generalize this approach, because in the early universe, we don't expect that we only have isolated star clusters. It's very likely that they are still embedded in gas, because we do have a lot of gas present in the early universe that can be efficiently accreted, and that often also in simulations we see that gas keeps infalling into these clusters even after their initial formation. So it's very likely that we can assume them to be embedded in gas. Then the gas provides an external potential. It reduces the crossing time, because if the stars are more or less virialized, they will then have faster velocities. And of course, this enhances the collisions, but at the same time, the gas can also be accreted onto the protostars and can further enhance their mass. And this is something we've explored initially with toy models and currently with more realistic simulations. And initially in our toy models, we considered different types of gas accretion. We had different types of extreme cases, ranging from an infinite gas reservoir to finite gas reservoirs, and position dependent and position independent models, and both time dependent and time independent models. So good, if you're interested in the details, it might be best to look at the paper, but I will give you here some of the main ideas. Here you basically see what happens, how the mass of the most massive object is evolving in our reference models. So this is a model where we have a Plummer radius of 0.1 parsec, an initial gas mass of 10 to the 5 solar mass. The initial stellar mass is small, like 10 to the 3, but we have like 1,000 stars in the beginning. And we assume here protostellar accretion rate initially of 0.03 solar masses per year, which then develops depending on the model and taking into account the available gas reservoir. In the more optimistic models, you see that you can get masses here of up to 10 to the 5 solar masses, so where even most of the mass is being accreted. while good in more pessimistic models, what happens is that the gas is preferentially accreted to the stars more in the outer parts of the cluster. Some of them still collide and contribute to forming a massive object, but good in principle, not all of them. And then here, in this case, we end up with a total mass of about 10 to the 4 solar masses. There's one restriction here that I should say, that we didn't include feedback yet at this point. I will soon show you also how feedback can change this picture, and then there are different processes that can reduce this mass to a certain extent. But this is, say, the most optimistic case if we don't consider any counteracting processes. In this case, good if you vary the parameters, if you study how does the mass depend on the gas mass and on the size of the cluster, it's relatively robust. So for the gas mass, it's a very weak and approximately, or good, it depends on the model scenario. For some models, it's quite robust. There are other models that are more sensitive to the actual gas mass. So the actual accretion physics, I think I should say that they actually do matter to a relevant extent. And you see that similarly if you vary the radius of the cluster. Good, similarly, we've been varying the total number of stars and the initial accretion rate in the cluster. So some of them have a stronger impact and others not as much. But you can get here some idea on the main parameter dependence. Now, one of the interesting things that we found recently, and a good one of the processes that can indeed counteract this, is if you have mass loss during collisions. If you have two stars colliding and then mass is being ejected, then in principle, even a moderate fraction of mass loss can make a relevant difference. We've parameterized this here with the fraction f of the mass that is retained in the collision, so the mass that is being kept. And we plot here the final mass as a function of our different models, for our different models as a function of f. And you see, good, of course, you get the largest masses if all the mass is retained. This is pretty clear. But then even if you have a few % of mass loss, you see that this steeply goes down. And that's a relatively important and strong effect. And why is it so steep? The point is that even if you consider just a few, or let's say 5%, then once you form a massive object and you regularly bombard it with small stars and merge, then what can happen is that the mass gain will be smaller than the mass loss, and the mass loss can at some point even outweigh the mass gain. And this is what brings down the mass of the most massive object here, and it provides a relatively natural limitation. And it shows that the mass loss via collisions is a very important aspect to take into account. What we've also been studying is more precisely how this depends on different physically motivated accretion rates. We've been studying constant accretion rates, Eddington accretion rates, Bondi accretion rates, and some different cases. I think I will skip this because we are short in time. What we've also looked at recently is what happens if we have winds, which can strongly affect the results. And in principle, the mass loss from winds can be a very significant limiting factors, especially at high metallicity. We show here, in principle, the solid lines show models for the mass loss, while the dashed lines here show models up here. This is Bondi-Hoyle accretion, so this is mass gain. And down here, this is what you expect from Eddington accretion. And you see that at a certain metallicity, the mass loss will simply outweigh the mass gain. So this provides a very natural restriction. And what we also showed more recently is the strong effect of the energy deposition from winds into the gas, which even at lower metallicities can still be a very strongly impeding factor. And essentially, yeah, for higher, or I mean, it's not even extremely high, but even for clusters with a metallicity of, say, 1% of the solar metallicity, you would still have a very strong feedback effect from the energy deposition by winds, which essentially restricts these scenarios to the primordial regime. Yes, one alternative that we are also working on, I can't go into the details of this for reasons of time, but one of the alternative scenarios is if you have massive star clusters, then the massive stars in the clusters could evolve into stellar mass black holes and form a black hole cluster in the center of a larger cluster. And there's quite a range of ideas now how also gas inflows into such a black hole cluster can lead to contraction and could lead to the formation of a massive black hole seed. So this is in principle another interesting alternative that that can provide a way to form massive black holes that are related to clusters. But yeah, to not go over time, yes, good. If you're interested, you can look at our book on the formation of the first black holes. So there you find more details on several parts of the physics of the first black holes. And otherwise, I will come to the summary. So to say that we've been looking here at different scenarios for the black hole formation. There is the scenario of direct collapse, where a lot of the mass goes directly into one single object. And good, at least in this extreme form, it is rather difficult, and there could be problems that we don't know if it will work frequently enough, because the main issue with this scenario is that you need to take care for very special conditions to ensure that you can sufficiently destroy the molecular hydrogen, and it may not happen frequently enough. There are, in principle, many alternative scenarios based on collisions in the early universe, which could be favored by the large protostellar radii, and many models predict that rather dense stellar clusters should form. And one thing that we are currently working on in more detail is exploring the interplay of collisions and accretion in the formation of massive objects. So to not only consider gas dynamics or stellar dynamics, but to bring both of these things together. And potentially this provides ways to form massive objects, but at least at high metallicity, there are also strong restrictions by the feedback effects from stellar winds. Yeah, and good with that at the moment. Yeah, I'm finished with the talk, and I'm happy to take questions.
Thank you very much for your talk, Dominik. Now it's time for questions. So if you have any question, please unmute yourself or maybe raise the hand.
Maybe I can start, Mario, with a very general question. I mean, it's general enough because I don't work on this, but one of the obvious ways of discriminating between different models is not via electromagnetic waves, but via gravitational waves. And I saw you mentioned this in your you had a chapter in the book about that. And in that context, I mean, people have been trying to do exercises of, I mean, of course, we don't have data because we need LISA to discriminate between these different models. People have been trying to do model selection exercises, so to try to see if simulated data can point towards direct collapse rather than collisions or accretion. Do you think the level of maturity of these models is sufficient to, when we'll have data in 10 years' time, to discriminate between these models? And this is the first question. And the other is even more naive. Some people they even put forward another channel for the formation of seeds, which is a primordial channel. Do you see any reason to invoke a possible primordial origin for the seeds, or do you think these models can explain I mean, all that we need to explain about the seeds of the existing massive black hole population at low redshifts?
Yeah, good. I mean, I'll start with the first question. So, I mean, I think, yeah, this is true. I mean, I think LISA can be, or also other gravitational wave observatories can be very important and help us to distinguish the models. I mean, I indeed, I know some of the work, and I think it's very important to do that. I mean, I think there are studies, or there is preparatory work that I think on some hand is very good. Like, I think people did quite a lot of effort to follow the cosmological evolution. If you start from a certain seed, how the black hole goes through mergers and which events can occur. One of the things that, I mean, good, one of my, in a sense, my criticism about it is that, I mean, there is, of course, well, one of the issue concerns the input data, because some of the scenarios that people have in the literature, they are now based on relatively old, and I would almost say outdated ideas for the formation scenario. And from my point of view, one needs to update some of this, and one has to see what happens if we change some of these scenarios, what if the parameters are different than what we anticipated, or what happens with completely new scenarios where it's not only collisions, or where it's not only black holes from the first stars, but if we have an interplay by collisions and accretion, for instance. And I mean, good, what I often see is that people focus, or they try to contrast a few very idealized cases, which in some senses may be understandable, or if you want to be able to get to a clear result, maybe you want to contrast two extreme pictures. But of course, from my point of view, of course, the truth could be somewhere in between, and there are many. I mean, from my point of view, I don't think we are at the end of this work. I think we have to update the models, and we have to include more realistic or different types of formation scenarios. And we also, I think also in terms of accretion, there are new developments like super Eddington accretion, which of course also need to be incorporated. And I think there are factors that could certainly still change the picture. So yeah, this for the first part of the question. Yeah, about purely primordial models, good, personally, I've never seen a strong motivation on that. I mean, I'm not really an expert on these models, so I don't know, I should maybe not comment too much on them. But I think there's at least a large range of physical mechanisms that I think could very likely work in one way or another. And I mean, unless one has a very strong motivation to consider a primordial mechanism, I would personally not tend to do it.
Yeah, but that's exactly, I mean, what I was asking, whether in your view, because there is no motivation for having a primordial origin from supermassive black hole, aside from the claim of those who actually propose that primordial formation channel, aside from their claim that the standard astrophysical channels are problematic. But from your talk, I gather that this is not what you think, that you believe a combination of these scenarios is enough to produce the initial seeds for the black hole population.
Yeah. I mean, I think certainly we have no reason to rule that out at the moment. And I think before claiming that we need primordial scenarios, we should be 100% sure that something else doesn't work.
No, and regarding updating the models, I totally agree. The models that we use for predicting how many sources there are for leads and so on and so forth. I mean, I totally agree. I mean, and this is in fact something that we could easily do if we have some predictions from simulations about the initial mass function of black hole seeds. I mean, we could easily implement this in the framework we use to predict number of Lisa rates and so on and so forth.
Okay, yeah, no, I think this would indeed be great. I think we, I mean, good, some of it, the thing is, I don't want to claim that our models are currently giving like the final result or so, but I think we could certainly think about some recipes that one could start with, or that one could directly.
So something more updated than what we have nowadays. Okay, well, thanks.
Yeah, sure, thanks to you.
So is there any other question? I see there is a raised hand by Sebastian. Go ahead, please. We cannot hear you, Sebastian, sorry.
Can you hear me now?
Yes.
Okay. My question is regarding the description of gravity. Are you using Newtonian gravity all the time, or also numerical relativity at some point? Because you also, I mean, you talk about black holes, and I guess these simulations take a long time and are very difficult to make.
Yeah, I mean, in most of our simulations, so typically we are in the regime where you can use Newtonian gravity. I mean, even though we talk about black holes, but as the very final stage. And I mean, most of our work concerns on how you get enough mass into a small enough region where then eventually the general relativistic effects may start becoming important. But good, what you typically expect, I didn't explicitly say that, but good, what typically you expect is you form first a supermassive star, which is already like at the limit of what we can properly model, and where we initially these effects are thought to be minor, but during its lifetime, the star will contract when it radiates away its internal energy. And then during the contraction, the general relativistic instability occurs, and then you collapse into the black hole. But that's something that we don't model, and which in principle we don't study ourselves. There is some work that we do that incorporates some relativistic effects, like I mean, we currently started a project with a master student who models now a black hole cluster. And this we do with post-Newtonian dynamics, or we do some work about radiation transport in black hole space-time. But I mean, that's not related to black hole formation.
Okay, thanks.
Okay. Any final question? Seems not. So then let me thank you again, Dominik, for your talk. We were very happy to have you here. And before we